The topic of this lecture is software design primary considerations. We are going to discuss what are the preliminary considerations when we design the software. What are the ingredients for the design process? So the first question that we have to address is, what is design? We have used this term in real life often. We say we design a specific device, or we have a design of a building. So when we say we have a design, it's a representation of something that is to be built. So we first want to model the actual, and it's a conceptual model that we call a design. This design has to be then converted into implementation. So design then gets converted into implementation. So it's very important that we design such that the design can be easily converted into implementation. So let's look at some of the examples of design in real life. We often see blueprints for a building architecture. If you have gone to an architect, you would see blueprints in front of him, or in your early engineering drawing classes or lectures, you must have created blueprints for few designs, your plans, for example, for the building, or your design of, in electrical engineering, you design your machines. Design is not the actual implementation, or design is not the actual machine. It's a model of the machine that you want to build. Various considerations go into this design process so that the design then gets transformed into the actual implementation. So blueprints for a building architecture. This is an example design. This manifests in the actual building later. This has to be then, the actual project has to be executed as per the design. This is another example of a design, a plan for conducting a workshop. You are conducting an event, and the actual event is your actual project, or you can say it's an implementation. But you want to first have the design of that event, and then as per the design you want to execute it. So we have an example here. This example shows a plan for a workshop. So this is a conference program. This is a program for a national conference on object-oriented technologies, which was conducted last year. And you can see that this has time slots, and various sessions have been organized into these time slots. So there is a tutorial on model driven development, and there are papers, and there are tea breaks, and so on and so forth, and there is also an evening tour, and on day 2 there are other papers and so on. So this is an example design. So a plan for conducting a workshop, it's also design. It's not the actual workshop that we see. First we have to plan for it, and then we have to execute the workshop according to the plan. So we have this design with us, but this design is slightly different from the design of a building architecture. This is about events, that is about structure. So designs have to be built for various kinds of activities that you have in mind, the dynamics and the statics and so forth. Another example design is the course syllabus. We have course syllabus for all the courses. That's the design of the course, and then the course has to be taught accordingly. The course is taught to cover the syllabus. So the design then gets converted into implementation, which is the actual teaching of the course. So these are example designs in real life. Now we know what are designs. Designs are not actual implementations. Designs have to be converted into implementations. So what are the considerations that go in designing software artifacts, designing software, and how do you carry out these design processes? So we will now focus our attention on design in software engineering. We can talk of the software development process as such, and also the product that we want to build. So how do you build the product? What is the process of building the product? Where are you going to start? How are you going to take your steps? How are you going to iterate? Where are you going to stop? And how do you document everything? How do you test it? How do you verify it? What is the review process? So this is the process of design, or process of software development in general. In that you have the design process. When do you actually design the software? How do you go about designing? How many people work on the design? How do they go about designing? Where do they start? So you have to design this process itself. Any process for that matter in the entire life cycle. First you have to design. So process design is an important discipline. This talks about design for the process of carrying out software development. You need to design the process just as you design the product itself. So product is that way different from the process. The process is the one that brings out the product. But you have to also design the process. When you actually carry out the process, that is the implementation of the process. So you have to plan for the process and then actually carry out the process, which is the implementation of the process. Similarly, you plan for the product and you actually build the product, which is the implementation of the product. So you can talk of process design, and you can also distinguish product design from process design. So process design is the design of the product to be built. In this lecture, we are going to focus on product design. But we will also look at some examples of process design so that you will get an idea about what are the ingredients of a process design. You might want to select the methodology that you want to apply in your processes. What tools are you going to use? When you select a methodology, your tools also might follow your selection. The project planning and execution plans, entire process of project planning. How are you going to execute? Your process standards and documentation standards. What are you going to follow in your entire software development life cycle? Your resource allocation charts. When are you going to use your specific software engineer? Where are you going to deploy them? Where are they going to work? On which site? Which are the machines that you are going to keep aside for the development? Which cabins are you going to allot to your teams? Where are they going to discuss? Resource allocation charts. Then how do you ensure your quality of your software development process and reliability of your product? What are the different methods that you are going to employ for quality and reliability methods? So these are all different ingredients of your process design. When you design your process, you take into account all these considerations, so that finally you want to actually follow this design and follow this method in your software development, so that you get the good quality product which implements what is desired, what is specified by your software requirement specification. Now we will switch on to product design. What is so covered in product design? We have seen process is different from the product. Process is the activity that you carry out to build the product. So now when we want to describe our product design, when we want to describe the design of the product, what are the considerations? What do you have to cover? You can talk of the product architecture. An architecture is a very overall design. It's a high level view of the design. Product architecture might be in terms of subsystems and its components, or various layers in your software. How do you describe architecture? That's a separate topic of discussion. What are the ingredients of describing architecture? On this slide we are going to look at different aspects of design. You might talk of the architecture, similarly you can talk of individual subsystems. You can design individual subsystems. What are the ingredients of individual subsystems? How are they interconnected? What are the different modules in your software? This is another design consideration. What are the packages and the libraries that you are going to develop as a part of your software? So your design might consist of module design, package design, design of the libraries below the subsystems. So at top level you can say you have a product architecture. A top level design is typically a high level architecture. Then you can talk of designing subsystems and interconnections among the subsystems. So you can talk of modules, individual modules, packages, libraries, and again interconnections among them. Then you can also talk of low level components and classes, the design at the level of components or at the level of classes. What are the specific individual classes and how are they connected? How do they collaborate? What do they do? You can also talk of file level design and executable binaries. When you want to actually deploy your software, you talk of executable binaries. You want to install the software and there are, say, in a typical Unix system you would have /bin or /user /include and so on. So you distribute or deploy these software binaries and sources under different directories and so on. So what is the architecture for this? What is the deployment architecture, or what is the specific design of your different files and how are they interconnected? How are the executables organized? This view is also important. Then you can talk of low level entities such as functions, data structures, and also algorithms. You have to design them. You have to design your functions, your data structures and algorithms. This is different from actually implementing them. The design may not go, or in fact it should not be code. Design is not code. Design is a high level specification of the implementation that you are going to build. So you can talk of functions, you can talk of data structures, you can talk of algorithms. Then if you have a very data centric system where you have persistent data in a, say, in a typical business application, you are developing your library information system or you are developing your academic system. You have a lot of data and there are again relations among them. You have tables. You convert your models into your relational tables. You want to design them, a table design or your data design you can say. This is also important aspect of your product design. Then at the high level of the product, so that's the user level. User wants to interact with the product. So how does the user interact with the product? What is the design of that interface layer? It's also important to see how the interfaces are organized. How is the user going to interact with the software? You have to design your interfaces. Interface design is an important aspect of your entire software design. Then these are other important considerations. Concurrency, design of your concurrent activities. Which are the concurrent activities in your software? Are they also parallel? Is there distribution? How are you going to distribute? What kind of architecture you have for your system? Is it a bus architecture, or do you have a ring architecture, or do you have a mesh, or If it's a parallel computing system, you may have further architectures such as hypercubes, specialized grids, and so on. So what are the aspects of design from the point of view of concurrency, parallelism, distribution? You can add to it replication, fault tolerance, and so on. What about your networking? How are you going to network your system? What are the protocols that you are going to follow? The physical and the logical layers. What is the security architecture? These are all very important aspects. Apart from the very core functionality of the software, these are also important. So you have to design for all types of requirements of the software, the functional and the non-functional requirements. The functional are those which are related to the actual, the semantics of the data and the operations on the data, and then these are non-functional requirements such as distribution, parallelism, your networking architecture, the security, how are you going to allow users to log in, what is the encryption mechanism, and so on. So all aspects of software development should be considered in the design process as well. Everything has to be designed so that finally at the implementation time you don't get surprises. It's very important to design everything before you actually implement. This is from a very purist point of view, but it may not happen in practice. Sometimes when you are implementing, you have to change your design, or you have to perhaps redo some parts of your design. This should be also possible. Your designs should be such that one should be able to refine them, modify them. So now we will look at those aspects of your designs. How should the designs be? What are the properties which must be satisfied by your designs? So before that, we have to note that designs are done after the analysis is done. You have to come to design from the analysis, and from design you go on to implementation. So during analysis, you have these products such as the entity relationship model or a data flow model or a use case model for the high level functionality point of view. The entity relationship model identifies the entities in the domain and they are connected, different relationships. Data flow model identifies the data and the flow of the data through different processes. Use case model identifies how the user is going to interact with the system, the use cases, the cases for the users. And there are also other different methods of analysis. I have included one here, which is agent oriented domain analysis model. What are the agents in the system and how they carry out different activities. Agents are mainly the animate agents, that is human beings. What activities do they carry out? You want to automate something, you want to automate an activity, a business model, then you have to first find out what are the different entities and agents, how is it carried out currently, and then you have to analyze this system, and then you can go on to design your software to automate that system which is already in existence. So you need to first analyze what is happening in the system. So analysis models are produced, and then using these analysis models you can build the designs which you translate into software implementation. So design models are built from analysis models. This is very important. And then design models can be easily mapped to actual implementations of the software. So now we will come to the factors that we have to consider during design. First and the most important factor is this: does your design meet the functional specification? First of all, is it meeting the functional specification? Is it complete? So this is the first requirement, that it meets the functional specification. Suppose in your library information system you want that the finds must be automatically calculated and the design doesn't account for it, then the design is not complete. This is the most important factor, that you have designed for everything. So how do you make sure of it? Who is going to test for this? The specification may be in, say, plain English or in a standard, the IEEE software requirement standard. Now somebody has to review and find out whether this design is meeting the requirement. So there are review processes to make sure that the design meets your specification. It covers everything, it's complete. How close is the design to the problem domain itself? This is an important aspect of a design. If the design is very close to the problem domain itself, say for example you have objects such as books, racks, users, different floors, journals, CD-ROMs, video CDs in your library system. In the design of the software, you could also have objects which have the same names. Now it will be very easy for even for the implementer to view what he is going to do. It's very close to the actual real life system. So this is an important aspect. This makes your design more understandable because it's very close to the actual system. How close is the design to the actual problem domain? This is also sometimes called seamlessness. Seamlessness is a property of having no bump between two different stages. If there is a seamless transition from one activity to another, you don't experience the bump or the jerk. It's seamless. There is no seam. So if you have a real life system and if you have the software domain, even the domain expert or the users who are currently operating the real system will be able to understand your design, or will be able to review it, or will be also able to comment on it, because the design is very close to the actual real system. The abstractions that you have used in the design have been taken directly from the real system. So this is an important aspect of a design. If it's close to the system, the real system, the problem domain, then it's easy to understand the design, easy to comprehend it, and also it's also easy to come up with a design. Many times you can have very the similar entities and the connections as you see in the real life, but this is not always true. For example, you have abstract classes in your design. So where do abstract classes come from? You are seeing some commonality amongst many different types of objects, and that commonality you are capturing in your design, but it's not there in the real life. But the actual objects, the concrete objects are there. The concrete classes will be the corresponding entities. The real objects can be mapped to the concrete, specific concrete classes in the design. So those are very close to the actual objects, but the abstract class, which might be a super class of your many subclasses, that abstract class you do not see in the real life, which is mainly in your mind, which is at the level of your logical organization of the objects. a category of objects. It's a logical organization that you have in your mind. Some of it might get manifested in the library system through your classification system, but not all the logical abstractions get captured in the real system. So the designer adds these additional abstraction in the design which are not there in the real system. But whatever is there in the real system, if you find corresponding entities in the design, it's easy to comprehend such a design, to understand such a design, and also to build such a design and then to convert it into an implementation. Another factor that you need to consider in design is that of performance. Is your design the best possible design from the performance point of view? You may not always get the best design because your resources are limited. You have a deadline in front of you. So you have to make a best attempt to get a high performance design which doesn't have performance bottlenecks. For example, there is a server that accepts requests from across the internet, and everything has to come at the server, and the server itself executes the responses and sends them out. Now this one server which accepts all the requests and computes the responses will be a bottleneck. Instead, you could have gone for parallelism and also distribution, so that in parallel you could have carried out many activities and responded to many requests simultaneously, making sure that your low level data is in consistent state. You must get a high performance design given your resources and time constraints. You have to account for it. In fact, this directly comes right from your requirement specification. What is the performance that you are expecting from this software, and you have to design for it. So performance is an important criteria. Completeness of the design, closeness to the problem domain, and performance aspects, have they been taken into account into your design? This is another important point. Is the analysis model traceable into the corresponding design model? So you have done data flow analysis, you have done entity relationships. Can you trace them into your designs? Can you show how an entity in the entity relationship model has been mapped onto another design entity? Where has it gone? Has it gone as an attribute in a class, or has it become a class itself? Are some collections of entities and relations being mapped to tables, or are they being designed as separate tables? Your data flow diagrams or the data flow model, are the processes being mapped to functions, or are they processes, servers which are active servers? A server typically goes in a loop. It is open for request. As soon as it gets a request, it operates on the request and sends the response back. So you have to trace this analysis into your design. Why is this important? First of all, the design is banking on the analysis model. The analysis has to be converted into the design, and then whoever wants to understand the analysis and the design has to go through this. If it's traceable directly, again this traceability has to be seamless, not without bumps. So if you use the same methodology for design and analysis, you might benefit from seamlessness. For example, if you apply object-oriented analysis and design processes, you use the same notations and the same meta models for your analysis, and you use the same notations in your design, then there is seamlessness. So what you start or what you come up with analysis, you further refine, and then it gets transformed into design. So this is another property. So it has to be first traceable, and if possible, if it's seamless, that's also another advantage. Now, when you design, are you designing everything from scratch, or are you going to reuse something which you already have? This is another important factor that you consider when you design your software. So when a software firm takes up a project, it may not be the first time that it has taken up the project, unless it's a startup firm. So you carry out designs often for different kinds of projects, different products. Now when you get something new, are you going to start from scratch, or are you going to look at your earlier results, earlier designs? Are you going to benefit from your earlier designs? If you have encountered similar situation earlier, you have to bank on some of the results of your earlier design process. How do you reuse? That's another question. Say if you have designed for a specific protocol, you can simply take that design if the protocol is recurring. You have to benefit from your old designs. There are mechanisms for reuse. There is a separate discussion on design patterns. Design patterns are the object-oriented designs which can be reused again and again for different domains in different applications. For example, you have this common design requirement that customers subscribe or consumers subscribe and publishers publish the results or publish events, and whenever something is published, the subscribers must get the results of the publications, or the events are to be delivered. So if there are services built, for example abstraction service, it looks at different newspapers and then it gives you an abstract of what has happened today to the subscribers. Now this is a common requirement, that there are publishers and subscribers. Now if you have encountered such a requirement in a design earlier in another project, and if this recurs in a different new project, you have to now use the results of your earlier design and directly apply it in the new project. The names of the entities might be different, there might be specialized behavior, but you should be able to make use of most of what you have already encountered. So object orientation does allow you to reuse lots of your design ideas, and there is a nice book by the Gang of Four, or the four authors which are called as Gang of Four. Eric Gama is the one who actually started this. He is one of the pioneering researchers who started discussions on design patterns, and the book got published, and that talks about reusable designs. Incidentally, a reusable design does not directly imply that the corresponding code is also reusable as it is, but at the level of design at least you should be able to reuse, and if there is code reuse, that is also possible, but most often your entities might be different and you have specialized behavior, so the amount of code reuse that you can have in your system sometimes is limited because of various considerations. But the point is that one has to learn to reuse your results of your old design processes if there are similar requirements. So you are reusing design and you are also reusing the design processes, because once you do designs again and again, once you design again and again, you also develop the process of designing. You also know how to go about decomposition, how to design your system. So the process also gets reused along with the product of the design. So reuse is an important factor in your design. Then we can talk about the design. Is the design well structured? How good the design is? Is there a good decomposition? Or is it very haphazard? It's very hard to understand the design. There are too many interactions. One doesn't know where to start. Such designs are not good for your health. You need to have well structured design. You have to have structure. Now what kind of structures are there? We are going to see it soon. Another factor that goes into designing is the evolvability of your design. Is it evolvable? This is very important because the requirements also keep changing quite often. Sometimes you have not considered all of them in one shot. Something is missing somewhere. You know it down the line. Now you need to evolve your design. So when you are designing, that time itself you must design such that the design is evolvable. One should be able to make a change into it very easily. There are techniques to build evolvable designs. For example, if you have already structured your different entities into a nice inheritance hierarchy, you will be able to add a new subclass into the inheritance hierarchy and evolve the design. If you already have a modular design, you will be able to add a new module into the design. So design has to be evolvable. You have to take into account future additions and future changes. There are different properties of specific designs that go into these main or major high level properties such as evolvability. Say for example coupling and cohesion and so on. These are software metrics. But that is not the focus of today's lecture. We are going to look at the basic core properties or the basic considerations into the design. So evolvability is very important. You have to design such that the design should be evolvable. One should be able to take a design and should be able to evolve the design. To be able to evolve, it has to be well documented. You must produce all the important documents or all the documents for the design. There are diagrammatic notations. You may also have text-based descriptions. You may also specify your designs. There must not be any dark matter left out. If you document well, then the rest can follow from the documentation. So documentation sometimes is mistaken as documentation for documentation's sake. Documentation is never for the sake of documentation. It is for the sake of all the goodness properties that you want to extract from a design. Evolvability, maintainability, its understandability. You have to produce proper documentation. How to document? Top-down approach must be taken. You have to start, you must have a high level document so that first quickly you can grasp what the system is. After you grasp the whole system, then you can zoom on to specific subsystems and then understand the system. So you have to document the design. No dark matter in software. You should not leave something dark. Something that is not documented is dark because you do not know what the system does. Another factor is that, have you reviewed your design? This is in fact about the process of designing. You have to review your design so that you must make sure that it's complete and you have not missed out anything and so on. So this is an important aspect of your design process. Now we'll look at the important process that you apply in designing complex systems, the important criteria or the important activity that you carry out when you want to defeat the complexity. That is by decomposition. In one shot you cannot get the entire design. In one shot you cannot start writing down the lowest level details of your design. Decomposition is very important. That's the way to beat any complexity, any problem that you want to solve. You should be able to decompose the problem into sub problems, solve them, and then connect it back. So decomposition can also be seen as partitioning. Split the system into many components and separate the concerns. So you might split the system into many components, but then there might be redundancies and lots of overlaps, so that it might result into a chaotic situation. Nobody knows who is doing what. It has been decomposed, somehow haphazard allocation of tasks have been done, but then there is no good protocol, or there is no consistency among themselves in what they do. So partitioning might have been done, but it is very haphazard. Such a system is not usable. You have to separate the concerns so that you have that modularity. Everyone does some specific task and it's not repeated elsewhere, and then they collaborate with each other. So you have to decompose into such a system. And then of course when you decompose, the decomposed components or the subsystems or the partitions or the parts must collaborate with each other. So there must be methods of composing them or connecting them or letting them collaborate or coupling them. So decomposition and composition are very important aspects, very important activities for doing complex systems design. You have to decompose, you have to separate the concerns, and then again connect all your design artifacts together. Connect the components and let them collaborate to achieve the system's overall functionality. So one can take a top-down approach to this, or one can take bottom-up approach to this. In a top-down approach, you start from a very high-level design description and then break it down further into different sub-designs or subsystems or modules, and then further break it down and go on designing that way. Or you can also start from very low-level modules and then build them up, put them into packages, and then go on to build the architecture. Top-down versus bottom approach. Top-down approach is good for starting from a high-level description and understanding. So it's good for documentation. But most often, if you don't have a clear idea about your design, top-down design also may not be possible. You may have ideas about the low-level modules and then you want to connect them. Then you could go about bottom-up design. But usually, so this is about top-down, start from high levels and decompose downwards, identifying connections, collaborations at every stage, or the bottom-up, start from lower modules and then compose them upward. But in practice, you may want to go back and forth. You may want to start at some top level, go down, and then you get something new there, and again build up, connect it back. So you may want to go back and forth. That is, you want to iterate upwards and downwards for different refinements. This is very practical approach. You start top down, and if you feel that now you have something more in the in the lower levels, lower layers, then you want to come back and you want to modify your top level designs and so on. So you can start from both directions, but top down design is easy to practice if you have a vision of the top level vision of the design. So one important property of top-down decomposition is that it gives you a good understanding of the problem. For documentation, Even if you have not practiced exact top-down process for your design, you might want to document, or you should document from a top-down perspective. Top level design document is the first one that the reader might want to read, might want to understand, and then you can go about looking at lower level modules and further zoom on. So top down documentation is very useful even if you have not followed the top down design. So composition and decomposition are the two important activities in designing. So we will now look at, zoom on to this decomposition activity. We have already seen that you need to separate the concerns through the modular decomposition. So we had also seen that there are different ways for decomposing. For example, these hierarchical structures you can build. The decomposition gives you a hierarchical structure. So what are the different ways of decomposing? You can decompose a system into a part-whole hierarchy. There is a big system and then there are parts inside the system. Or you can decompose the system into an inheritance hierarchy or an ISR hierarchy, classification system. A part-whole hierarchy, for example, there is a computer, and in the computer there are different parts, and or the different IC chips and the cards and so on. So in the computer there are cards, there are monitors, there is a keyboard, and the cards have IC chips, and then so on and so forth. So you can give a design in a part-whole system. What are the parts of the card and what are the parts of the chip, and then go on further. Or you can take a classification hierarchy or an inheritance hierarchy or is a hierarchy. Another way of decomposing is the instance of hierarchy, the types. A is a type of B, B is a type of C, and so on. In languages like Smalltalk, you have objects, classes, classes of classes, there is meta classes, there are meta classes, meta classes. So that is another way of decomposing the system. Or another orthogonal perspective is that of focus of attention, zoom. So you have a high level design and then you go on to a lower level and zoom on to that, and you further zoom on to that. So you get this structured decomposition. So there are different ways of structuring your designs. For example, this focus of attention hierarchy in UML, the state charts, you can zoom on to a state and give a separate state chart for the state. So this is a way to decompose your system so that you will be able to understand it first at the high level, at the top level, and then further go on downwards and zoom on to your subsystems or your subdesigns. And then what about composition? So we know now these are the different ways of decomposition. What about composition, interconnection or collaboration and coupling? How do modules correspond with each other? What is the best way for them to correspond with each other? Should they interact with each other too much, or should you minimize that, or should there be no interaction? Without interaction, how can they collaborate? How can you have a system with many modules? How good is a given modular decomposition? What is the goodness property? So there are metrics to measure the goodness of designs. So there are different ways for modules to interact. You can have, say, functional interfaces. If you have processes, you have sockets, or you have remote method invocations, or you have services on internet. Amongst functions, you call functions, function calls. There are recursions, coroutines. There are different ways of interactions. Some of these have been listed here. There could be peer-to-peer interaction. A communicates with B and B also communicates with A. A can send a message to B, B can also send a message to A. This is not about just reply, this is the message that originates and asks for a service. A asks for B's service and B asks for A's service. That's peer-to-peer way of connecting. You can have client-server model for interconnection. The clients ask the servers to provide a specific service. They send out a message and they get a reply in return. You have specialization, generalization for interconnection. Inheritance type of connection. You have aggregation for part whole. You have different ways of messaging. Message queues, sockets, blackboards. You have synchronization methods, signaling, semaphores, monitors. So different ways of interconnecting system, composing them. Once you have decomposed, you have to connect them. So composition and decomposition, or decomposition and then the composition of the composed, the decomposed modules or the entities, the interconnections and the collaborations among them are very important. And there are different ways of making them collaborate, different ways of connecting them, and so people have studied different kinds of connectors, and we all use different kinds of connectors for connecting different types of entities. So those have to be considered in your design. Now we will look at the basic principles that you apply during your design, so that all these factors get considered. What are these guiding principles? We must have come across some of these terms in real life or in your software engineering or in your object oriented programming classes or basic programming classes. Abstraction, encapsulation, refinement and communication. If you apply these principles in your design process, you will get many of the good properties of designs. If you measure the designs, the goodness criteria, the goodness properties will be brought out. If you have applied these rightly, if you have applied the principle of abstraction, the principle of encapsulation, the principle of refinement and communication in your design process, then automatically you will benefit from the guarantees that these provide. Now we will look at the properties of these basic guiding principles one by one. Abstraction. What is an abstraction? Abstraction is an external view of a given system. You want to understand what the fan does. You want to understand it from the high level perspective first, and then go on to, so you want to abstract it out, abstract what it does from the external point of view. You are operating specific buttons, you have a washing machine, or you want to operate a microwave oven. You have the external perspective, the interface. There is an external abstraction. So user's abstraction is different. The person who actually builds the microwave, his abstractions may be different. So the principle of abstraction has to be applied for different roles. To understand a lower level system through abstraction that is easy to comprehend is very important. Any system, if it is seen from an abstraction point of view, that is the external view of the system, you can understand the system well. Not only understand, but also for manipulation, an abstraction is important. Say data structure like stack. You can think of a stack in terms of the behavior of its push and pop methods. Whatever is pushed goes on top of the stack, and whatever is popped comes out of the top of the stack. Now when you describe this behavior, you don't worry about how it is implemented inside. What is the data structure used? Is there a linked list or is there a static data structure? How many pointers are you using? How are you incrementing them? How are you initializing? Are they automatically initialized by the language itself? So these are the internal views, but when you want to describe the data structure, you want to describe it from the abstract point of view, or from you want to describe it as an abstraction rather than an implementation. And then using these abstractions you can manipulate the system, because they are the abstractions for manipulation and also access. So given an abstraction, you understand the system and then use the abstraction to manipulate the actual instance of the system for which you have described the abstraction. So we use this principle of abstraction in your day-to-day programming practices. Types and variables, functions, classes and objects, files and processes, control constructs such as if then else, repeat until, for, or sequence statements. These are all abstractions, control data abstractions, packages and so on. So use these abstractions and then build your system. So these are programming, abstractions programming. But for your given problem domain, you have to find out the abstractions in the problem domain. Now how do you describe these abstractions? You can use abstract data types, you can describe them through interfaces, you can also describe the exceptions or the exceptional behavior that the entity will project. Suppose you are asking for a service, and if the server is unable to provide the service, what is the behavior that you expect from the server? This is also part of the abstraction, because it's an externally observable behavior, the exceptions that you are going to expect from service. What are the messaging protocols? What do you send first, and what do you send later, and what is the expected response? The protocol, the handshakes can also be part of the high level view. The contracts that are provided, preconditions and post conditions. When you ask for a service, what is it that is expected from you? What are the parameters that are expected from you? And what is guaranteed to you in return? Preconditions and post conditions. These are also part of the contract or the abstraction of a given entity. Then comes the principle of encapsulation. Encapsulation talks of hiding lower layers. This is for security and also for enforcing the abstraction. You hide lower layers on top of the higher level. Examples of encapsulation is local state within local scope, non-exported or invisible variables, private member functions in your classes, in your object-oriented programs. So encapsulation is manifested. You want to hide something so that you want to only project the external abstraction that you have thought of to the users, and the internal implementations are hidden. You want to guarantee it, you want to enforce it. So it's not enough to simply implement the abstraction, but it's also required that you enforce the abstraction through the principle of encapsulation. Refinement. Iterative refinement of a given concept should be easy to achieve without much redo work. How do you refine? What are the principles of refining? What are the ways of refinement? How are you going to apply this into your designs? For example, a software process with revisitable design phase, you can come back again and again in the process. You apply this iterative refinement. Or also you apply refinement through inheritance. You want to refine your subclasses, your superclasses to subclasses. You can apply this open close principle for components. Implementation is open for refinements, but the interface is closed. The contract is guaranteed. You can change the implementation, you can make it better. You can refine your implementation. That means in the next version of a component, you give a refined version of the component. The implementation is better, or it might be also specialized through inheritance. So refinement can take place through inheritance or through open close principles by changing the implementation without affecting the contract that you have exported or guaranteed for the outside users. Another application of refinement is in zooming. You want to zoom and refine. That means from macroscopic model you want to go to microscopic model. You are refining the model. You are refining the microscopic to the macroscopic to microscopic. The microscopic model is a refined model. State diagrams, for example, in UML can be refined or can be zoomed onto. There is a fourth way of refinement, that is generic descriptions. You have generic classes, you can refine them for specific types. This is different from inheritance. Template classes in C++. So refinement is very important for a change process, or even for expansion, for evolution, and as well for understanding and organization. The change processes are provided to carry out refinements. These also depend on what are the abstractions that you use for your refinements. So the examples are inheritance mechanism, encapsulation, and separate compilation of different files, and you can refine independent components separately, or you can blow up your models and refine them from macroscopic to microscopic point of view. And then finally, the aspect of communication. Different kinds of interconnections. We have to know the different types of connectors and how to make use of them effectively in your design. So interconnections, they are also called different kinds of connectors. The components collaborate through these connectors. So you have to use the right kinds of connectors. Interclass connectors, you can use pointers, references. Interprocess connectors, you can use sockets, proxies. Intermachine connectors, you can use TCP/IP, internet, and so on. And for synchronization, there are different kinds of connectors, pipes and filters, and so some more connectors have been listed out here. Shared memories, blackboards, semaphores, message queues, monitors, signals and actions, filters and pipes. So there are different ways of using these communicators or connectors amongst the components that you have designed. So finally we will look at this summary slide, what we have seen in today's lecture. We looked at what is design. Then we looked at some examples of designs. We had seen one example of design of a workshop, a real life process. Then we know that analysis is to be converted into design. Then we have seen different factors to be considered during design. We have also seen the advantage of a top-down process of design, and we have also seen that you can go back and forth in the design process from top to down, back to top. Then we looked at the basic principles to be applied during design: the abstraction, encapsulation, refinement, and communication. Thank you.